Hi everyone! This video looks at a weak acid titrated with a strong base, and will focus on the pH calculation before the equivalence point, which is called the buffer zone. If the titrant volume in the problem is more than 0 milliliters, then we have to set up a millimole table. The E row of our millimole table tells us where we are on the titration curve and guides us as to how to calculate the pH from that information. In this sample millimole table, we are only looking at the E row. Here we see that hydroxide is used up and that the solution contains both the conjugate acid HA and its conjugate base A-. Whenever we have a solution containing both conjugates, we have a buffer. This means that our reaction progress is in region 2 of the titration curve, which is called the buffer zone. HA and A- can be any values, as long as they are both greater than 0. Here, we're looking at the situation where they are not equal to each other. Because we have both HA and A-, we can use the Henderson-Hasselbalch equation, which is pH equals pKa plus the log of the conjugate base over the conjugate acid. Because our log term is a ratio, A- over HA, we can use any units as long as they're the same, which means for us that we can plug in millimoles directly and don't need to calculate molarities first. We need to make sure that we're using pKa in the equation, so if we're not given pKa, we may need to calculate it first. In our example, we see that we have more than 0 mils of titrant, so this tells us that we are going to need to set up a millimole table. Our millimole table includes the reaction that is occurring between the weak acid, HA, and the titrant, OH-, to form the conjugate, which in this case is a conjugate base, A-. Our rows are I, C, and E, initial, change, and end, and our units are millimoles. We're given molarities in the problem, and so we are going to need to calculate millimoles. For our HA, we have 12 milliliters. Make sure you include the zeros. 12 milliliters of solution times the molarity of the HA, which is 0.0500, and that's moles of HA divided by liters of solution. Liters of solution will cancel, and we're left with milli and moles. Looking at our sig figs, we have 4 sig figs in the volume, 3 sig figs in the molarity, so our millimoles will be rounded to 3 sig figs. Doing the math, we have 12.00 times 0.0500 rounded to 3 sig figs gives us 0.600 millimoles of HA. We'll do a similar calculation for millimoles of our hydroxide. Here we start with 5.86 milliliters of solution times the molarity of the sodium hydroxide, which is the same as the molarity of the hydroxide by itself, 0.0800 moles of OH- divided by liter of solution. Liters of solution will cancel, and just like the HA, we'll be left with milli and moles. For our sig figs, we have 3 sig figs in our volume, 3 sig figs in our molarity, so our millimoles here will also be rounded to 3 sig figs. For the calculation, 5.86 times 0.0800 rounded to 3 sig figs gives us 0.469 millimoles of OH-. Now we can fill in our millimole table. We have 0.600 for HA, 0.469 for hydroxide, and we're starting with 0 of our conjugate base A minus. We subtract the smaller number for each reactant, and then we add that same number to our product. So our smaller number is 0.469, so we'll subtract that from HA and from hydroxide, and we need to make sure we add it on the other side. The calculation here is subtraction, which means we need to keep track of decimal places, not sig figs. So for HA, we have 0.600 minus 0.469 to 3 decimal places gives us 0.131. Hydroxide goes to 0, and A minus is 0.469. At this point, the recognition of the E row of the millimole table is telling us that we have HA and A minus, both greater than 0, which means we're in the buffer zone. Because we're in the buffer zone, we can use the Henderson-Hasselbalch equation, which is pH equals pKa plus log of the base term A minus over the acid term HA. We can plug in the millimoles directly into the log term. The other part we need is the pKa. And we weren't given pKa in the problem, we were given Ka, so we're going to have to do that calculation. pKa is the negative log of the Ka. So to calculate pKa, we take the negative log of 6.3 times 10 to the negative 5. This is a measured value, so we do need to keep track of the sig figs. We have 2 sig figs in the log term, which is going to give us 2 decimal places after we take the negative log. So taking the negative log of 6.3 times 10 to the negative 5, we end up with pKa equals 4.20. Now we have everything we need to plug into the Henderson-Hasselbalch equation. pH equals pKa, 4.20, plus log of A minus 0.469 divided by 0.131. Taking a look at our sig figs in our log term, numerator and denominator each has 3 sig figs. So when we take the log of 3 sig figs, we need to keep 3 decimal places. Now it turns out that doesn't really matter because we only have 2 decimal places coming from our pKa. Because the final part of the calculation is addition, we need to round to the fewest decimal places. So when we do that final step, we'll need to round our pH to 2 decimal places. However, it is a good idea to keep track of the sig figs properly as you go along, just to make sure that you are actually retaining the precision of the measurements and of the calculation. So I'll take care of the log term first, 0.469 divided by 0.131, and taking the log of that gives 0.554, and so the math is 4.20 plus 0.554, and rounding that to 2 decimal places gives us 4.75 for our final pH.